So in this question, we have there are two cars. They're traveling at the speed limit of 60 kilometers per hour, but in opposite directions. So let's annotate the drawing. We have we'll make the right positive and the left negative. So this has a velocity equal to minus 60 kilometers per hour. And on the left side, we have a velocity equal to positive 60 kilometers per hour. The truck has twice the mass of the car. So we have a car with a mass m, and the truck has a mass 2m. The vehicles collide head-on and become tangled together. So afterward, we have this jumbled mess. So we have particle and particle beforehand, P0, and afterward, we have one particle. Two particles become one in terms of the collision. And of course, whenever we're thinking about collisions, we should be thinking right off the bat, this problem is probably related to momentum. So they collide head-on and tangle together. How do the forces of the car on the truck and the truck on the car compare? Exerted by the car. So what we're dealing with here is Newton's third law. For every force, there's an equal and opposite force. For every action, there's an equal and opposite reaction. So that's our statement. We've stated the answer, but now we need to explain why this is the case. Well, there's no law of conservation of forces or anything like that. We have Newton's third law, but why should that be the case? Well, the law of conservation of momentum means the total momentum of the system remains constant. That means the initial momentum equals the final momentum. So any change in momentum to one object, the other must have an equal and opposite change in momentum. Those changes occur over the same period of time. So delta P over delta T are also equal and opposite. The definition of force is delta P over delta T. So if delta P over delta T are equal and opposite, F are equal and opposite. And those are the pieces. So in what direction will the entangled vehicles move after the collision, or will they be stationary? Well, let's check this out. We know the law of conservation of momentum is the initial equals the final. And beforehand, we have the momentum of the car plus the momentum of the truck. And that's going to be equal to the momentum of the car truck. Now, so whatever the momentum is initially is going to give us the overall result. So we've got an MV for the car. So M times 60, so 60M. And the momentum of the truck is 2M times minus 60. And what we find then is we have minus 120M plus 60M gives us minus 60M. So since the P0 is negative, P afterward will also be negative. Therefore, moving to the left. It can't be stationary. Afterward, momentum equal to 0 because the P0 was not 0. And now we've done an incredibly thorough job of answering that question. Next, we want to determine the speed in kilometers per hour of the combined wreck immediately after the collision. So we'll pull this out down below. And so we already did a little bit of this. P0 equals P. And we have the mass, the momentum of the car plus the momentum of the truck is going to be equal to the momentum of the car truck. And so this is mv, mc, vc plus mt, vt is going to equal the mass, which is going to be 3m. Now the mass of the car is m, and it's 60, and 2m minus 60. So we're left with m with minus 60 m is going to be 3mv. So v is going to be minus 60m over 3m, which is minus 20 kilometers per hour. So it's interesting in this case, it doesn't matter what the masses of the cars are, just the ratios of the masses to give us a speed of minus 20 kilometers per hour.